So I hope you already understand the concept of force vibration based on the fixed base and also excitation base. Uh, so today we're gonna take a look at the response due to rotating unbalance. We are still talking about force vibration of a single degree of freedom system, but we want to take a look at the rotating unbalance problem. So make sure you know how to differentiate between these three cases and know which equation to use basically. So let us take a look at the system. So hopefully throughout this lecture you know the difference between this case, okay, and also the previous case in terms of the mass acted upon a constant harmonic force and also the mass acted upon by a frequency dependent harmonic force. So it is slightly different than the previous lecture where you take a look at base motion, which the input is displacement. This one, the input is still force, but it is based on rotating unbalance, and we want to take a look at how do you get the equation of motion or obtain the equation of motion. So this is concerning a special case. So maybe a good example, I always tell my students that some of the good examples may be the one that occurs in your home, which is your washing machine. So in industries, mainly common in rotating machinery, especially if you have problem of balancing, so you can get this rotating unbalance. But maybe at home, maybe a washing machine will be a good example. So now instead of just having a constant force like the first case, okay, F naught sine omega t, so we have an imbalanced force basically from the maybe unbalanced rotor or mismatch of the shaft connection. So you actually have the force in terms of me omega square sine omega t. So let us take a look at the model. How do you draw the model and how do you derive the equation of motion? So this is the figure basically. When you have here you can see that this is the center point of the machine, and you have a mass here. Okay, this is what we call the unbalanced mass. Okay, so this m here is what we call the unbalanced mass. So this mass is modeled to be located somewhere what we call E, or at the eccentricity distance. Okay, so the unit of E is basically in terms of meter. All right, so this thing is rotating. So you can imagine maybe in your washing machine you would have your clothes are clumping at one side. So this thing is rotating, that causes the unbalance of your dryer or your washer. Yeah. So at the same time, this mass, we call it as capital M. So it actually moves at a displacement x. So your input now is in terms of this small m, okay, at a angular rotational angular of omega t. So that's the explanation of this figure. So if you take a look at the basically the relationship, x is the displacement of the non-rotating mass, okay, which is m minus m, because you have to differentiate between the capital M, which is the machine, and the small mass, which is the unbalanced mass. So the displacement of m is therefore given by x plus E sine omega t. If you remember, you have some the mass is at the end like this. So basically what it's saying, okay, this point here actually experience a displacement of x. Okay, let's say this original position of the center of your rotating machine just now. So this is x, and there is another angle of rotation here. So if you want to draw here, basically this displacement is E sine omega t. So basically the displacement of this M is actually x plus E sine omega t. That's how it displaces, yeah. So the way to write the equation, the total, the mass that we are interested in is the non-rotating mass, which actually accelerates at x double dot. Then you are talking about this small m, okay, which is the unbalanced mass, which is actually, you cannot write it as x double dot because it's not. It is both x and E sine omega t. So that's why in order to put in the correct notation in terms of second derivative, we have to use this notation, yeah. So which is equals to, so if you look at back to this figure, so your x is going up. So if you want to draw the free body diagram, so this is actually very similar to your k, because these two k, you just add them up, so it's just k and your c, isn't it? So of course you draw in the same direction. Your k and your c will go up same direction as your x here. So then you have action reaction going down on this big mass here. So you can see that it's opposite of your x. So this is negative, this is also negative. So if you write, so it's kind of like this whole thing is that equivalent mass x double dot, something like that, right? So that's what it is, equals to summation of forces. It's actually summation of forces. So that summation of forces, you have negative kx and negative cx. So that's what you have here. It's a negative. You don't put the negative here. So you have cx dot here. But both are negative because it's opposite sign of your x. So that's why here you have negative. So then from there you can rearrange the equation, and you can see the difference between this case and the fixed base. So that's what we want you to make a differentiation. So if you remember, you have your fixed base equation, which is mx double dot plus cx dot plus kx equals to f naught sine omega t. So let's say I use sine, assume, because I want to match this one and this one. So you can actually see that the force here is equivalent to this force. So this small m is actually this capital M, and the rest are the same, isn't it? So quite similarly, so that's why in your equation for fixed base last time, you have a similar equation. This was F naught. So the main thing here is you have this as small m. Okay, then the rest are exactly the same as your fixed base. So we are actually comparing the fixed base case as with the rotating unbalanced case. Okay, so hopefully you can understand the different the purple color is basically the variable that we use in the fixed base case. Okay, so then from there you can actually get the steady state solution. So you also use the same or similar equation that you would use in the fixed base, but now we change a little bit because it is as a ratio of m capital X over me. All right. And you have this response of rotating unbalance. So now we are comparing the base motion and the rotating unbalance, which is case number 2 and case number 3. Okay, the first case is your fixed base. Yeah. So there are 3 cases basically. So here in the figure is what it's saying is basically for base motion and rotating unbalance. Although base motion, the input is displacement. This one we already changed it in terms of forces. You can see that the figure or the graph is exactly the same. Okay, you can actually get the R value, estimate the R value when it is equal to 1. Okay, greater than 1. Then the corresponding value of mx, you can get the maximum value of the amplitude. Okay, that refers to this axis, but the figure is still the same. All right. Other than that, for zeta is greater than 1 over square root of 2, mx does not attain a maximum. So in other words, you can see that you can see that there's no maximum value beyond this area, isn't it? They define it at a value of 1 over root of 2. At zeta 1 over root of 2. Okay, there is no maximum value. Okay, so then we take a look at the example. Okay, we have centrifugal pump weighing. So this is actually your mass. You have to divide by mg to get your mass. So basically your mass is equals to 600 divided by g. Then you have operating at 1000 rpm. Okay, so you can get your omega, which is 2 pi times 1000 rpm. Okay, divided by 60. Then you have 6 springs of stiffness 6000. So you want to find the maximum permissible unbalance in order to limit the steady state deflection. So the steady state deflection given is 5 millimeter peak to peak. Okay, what does it mean by that? So basically when you have a value of peak to peak, that means this value is half of that value. Yeah, this is peak to peak, which is 5 mm. So basically the steady state deflection is actually 0.25 mm. Okay, so we can take a look at the values here, your m. Okay, and then you can calculate your angular frequency, 2 pi times rpm over 60. The equivalent spring is you have to times 6 because you add them up. Then you can calculate your omega n and also your forcing frequency, because they give to you the omega already, and then from there you can calculate the unbalance. So what it means by the unbalance is actually me. Okay, so m is the unbalanced mass, but unbalanced means is Fe. E is the distance, unbalanced distance, okay, from the rotating point, or eccentric distance is the same. So Me is the multiplication of both. So the unit is kilogram meter. So make sure you know the difference. So when you read the question, you have to be very careful what they want to find. So here they want to find the unbalance. So the unbalance means it's ME. Alright, so okay, that's all for this lecture. Thank you.